Welcome to the intriguing world of covalent bonding, where atoms come together not by transferring electrons, but by sharing them. Imagine a story where atoms are like best friends, holding hands by sharing their electrons to achieve stability. Let's dive into this fascinating narrative to explore how covalent bonds form, their properties, and their significance in our everyday lives. At the heart of covalent bonding is the quest for stability. Atoms strive to fill their outer electron shells, achieving a stable, low-energy configuration. Instead of giving away or taking electrons like in ionic bonding, atoms in a covalent bond share one or more pairs of electrons, creating a strong connection between them. In the world of covalent bonding, the main characters are nonmetals. These elements are found on the right side of the periodic table and have a high affinity for electrons. Common nonmetals involved in covalent bonding include hydrogen, H, carbon C, nitrogen, N, oxygen, O, phosphorus, P, sulfur, S, and the halogens, fluorine, chlorine, bromine, iodine. When two nonmetals approach each other, they engage in a delicate dance, sharing electrons to fill their outer shells. Here's how it works. Single covalent bonds. Example, hydrogen, H2. Action. Each hydrogen atom has one electron and needs one more to achieve a full shell. By sharing their single electrons, two hydrogen atoms form a single covalent bond, creating H2. This shared pair of electrons holds the atoms together. Double and triple covalent bonds. Example, oxygen, O2, and nitrogen, N2. Action. Oxygen atoms share two pairs of electrons to form a double bond, resulting in O2. Nitrogen atoms share three pairs of electrons to form a triple bond, resulting in N2. These multiple bonds are stronger and shorter than single bonds. Molecular compounds. Example, water, H2O, carbon dioxide, CO2, methane, CH4. Action. In water, an oxygen atom shares electrons with two hydrogen atoms, forming two single covalent bonds. In carbon dioxide, a carbon atom shares two pairs of electrons with each of two oxygen atoms, forming two double bonds. In methane, a carbon atom shares electrons with four hydrogen atoms, forming four single covalent bonds. Covalent compounds exhibit a range of properties that differ from ionic compounds due to the nature of their bonding. Low melting and boiling points. Covalent compounds often have lower melting and boiling points compared to ionic compounds because the intermolecular forces holding the molecules together are weaker than the ionic bonds holding ions together. Poor electrical conductivity. Covalent compounds do not conduct electricity in solid or liquid form because they do not have free-moving charged particles. Exceptions exist, like graphite, which conducts electricity due to its unique structure. Variable solubility. Covalent compounds can be polar or nonpolar, affecting their solubility. Polar covalent compounds, like sugar, dissolve well in water, while nonpolar covalent compounds, like oil, do not. Softness and flexibility. Many covalent compounds, especially organic compounds, are softer and more flexible than ionic compounds. This property makes them ideal for forming materials like plastics and fabrics. Covalent compounds are everywhere, forming the basis of organic chemistry and the materials around us. Water, H2O. Essential for life. Water is a polar covalent compound with unique properties, like high heat capacity and surface tension, critical for biological and environmental processes. Carbon dioxide, CO2. A key player in photosynthesis and respiration, CO2 is a linear molecule with double covalent bonds, crucial for life on Earth and industrial processes. Methane, CH4. The simplest hydrocarbon and a major component of natural gas. Methane is a non-polar covalent compound used as a fuel and a building block for more complex chemicals. Glucose, C6H12O6. A simple sugar and energy source for living organisms. Glucose is a polar covalent compound that forms the basis of carbohydrates in our diet. Covalent bonding is essential for life and technology, forming the foundation of organic chemistry and many materials we rely on. Biological molecules. Covalent bonds are the backbone of DNA, proteins, carbohydrates, and lipids, which are the building blocks of life. These bonds allow for the complex structures and functions necessary for living organisms. Synthetic materials. Plastics, synthetic fibers, and many pharmaceuticals are made from covalent compounds. Understanding covalent bonding allows chemists to design and create new materials with specific properties. Environmental chemistry. Covalent compounds play a role in environmental processes such as the carbon cycle and the formation of ozone. Studying these compounds helps us understand and address environmental issues. Covalent bonding is a fascinating and fundamental aspect of chemistry, illustrating how atoms share electrons to achieve stability. This type of bonding leads to the formation of molecules with diverse and unique properties, from the water we drink to the DNA in our cells. Through the sharing of electrons, atoms form covalent bonds that create the complex and varied world of molecular compounds. These bonds are the key to the diversity of life, the development of new materials, and the understanding of natural processes. So, next time you drink a glass of water or marvel at the beauty of a plastic toy, remember the incredible story of covalent bonding. A tale of atoms sharing electrons to create the wonders of our world